So should I put quantum game theory in my next game theory or not? I have to work. I don't know anything about quantum game theory. In order to, the best way to learn is to teach. Don't forget that. Okay? It will take me a lot of time to figure out whether or not. But I would say option theory is part of that. The second thing I want to say is the following. Before we continue everything. The famous theorem in computer science is what? That's the biggest theorem in computer science. Computer science, including quantum, that is we want to context. It's only about one thing: how fast you can run the program. Each program takes you 10 years to run through. So P means polynomial time, and P means non-polynomial time. So if it's a polynomial, then it's fine. If non-polynomial, they call it NP hard. They call it NP hard. This is a big problem. The question is, when this equals this, you want to see my proof? Only one line. Even only here. That's the biggest joke in computer science, okay? N is not a number, N means not polynomial time. So in order to, all they want is whether or not something is FP can become P. P means that you can do polynomial time. Okay? That you can run 1 day or 2 days, but not 10 years. Okay? So what we are going to do, you try to follow it. One of the things that people like to do quantum computing is that many problems NP in classical computer turn out to be P with quantum. Okay? There are two algorithms completely in here for you to look at this. Okay? There are two. Let me show you first. Okay, we are looking at two. This chapter is on P and NP, everything in here. Okay? P or NP. How can you do this? Is about this chapter, only 10 pages. You have to read. It's called quantum algorithm. Okay? And they have two algorithms, which the problem with is NP for the classical computer turn out to be P for quantum computer. That's the first thing. Secondly, if you have a chance to look at that, I want you to look at some of the algorithms on the notation. No need of understand or run the algorithm. First of all, is can you understand what the symbol and everything is? That's what I like. So after this, you look at this, it's not weird for you. When they write out algorithm with all these symbols, you are not just familiar. When they write some symbol, just like a plus or minus, you will have to go to okay, before I go, any question for the last lecture? Okay, so let me give you the program. If you look at the handout, this is the part 1. That kind of it's about meaning and symbol in quantum computing. After that, you should be able to read and need to know the meaning. You might not understand, but you can read. Okay? The next two seminar is about modeling with quantum computing. And the part 3 is 4 times next one. That will be the end. It will be the new model called Black Littleman model will improve the top rank model that people are very familiar here to do for finance. Any questions? Otherwise, let me start from zero. Okay, first of all, remember don't worry, but you have to get in with that because they are going to talk about renewable space all the time, so we should not be scared of things like that. It's very simple, just the name of the so let me look at see it. Okay, see the complete number. Everything in here is like a vector. Okay, compared. Like a vector of n components, but each number here is a complex number. Okay, that's what the space here. Remember, Rn means fifth of x1, xn, but they are all real. So the difference is only this allowed to be complex, and we know why, because I can cube. So on this one, first of all, the Arab notation. I'll tell you what it is so you can read it and understand why we did Arab notation. So first of all, the point in here can be written in two different forms. They are completed objects. If you have a vector, let's say psi, it's a vector in here, but you draw it out at a get vector. That means it's a column vector. But in order to say a column vector, you have to tell me the basis of this one. Okay, just like an axis, like R3. So you have in R3, so you have a 3 axes. Okay. So if you have a point in here, point in M, it has, in order to find this one, it has X, it has whatever Y, it has a Z. But I can choose another one. I can turn this around. So you have to specify the basis when you write out like this, where it comes from. This is the get. Now, the graph vector in the transpose, in the row. Why is that? Because when you have two vectors in here, let's say, right, you have another point. You have two one, you can form the inner product that everybody knows. That's why it will be summation from 1 to n, let's say, conjugate, y. That is the strata product. And why that is important? Because if x is 0, that means the vector x is orthogonal to vector y. Orthogonal is the main thing why we talk about Hilbert space in quantum computing. If you don't have that, you cannot say something is orthogonal to another one. Because you know that, normally in two dimensions, this is equal to this one is equal to the product of the two distance times the cosine between two vectors. So if it's 0, that means both sides theta equal to 90 degrees. And if you put them together, okay, this is eclipse in front of bracket. It's a bracket. This symbol is a bracket. So bracket so this half of it is called the graph. You can call graph if you like. Okay, but you have called it graph. And in this part is called the ket. Okay? So the ket vector is a column vector. I want to write that. And the matrix. This is n plus 1 matrix. Because vector is special kind of matrix. Okay. And graph vector, the other way around. This is 1 cross n matrix. Row vector, row vector. It's very important because in this one, you can multiply. This product is a multiplication multiply by n. Now we have two things. We have bracket. So the question is, can you multiply? Okay, we have bra times ket. How about ket times bra? How about ket? And how about bra? Yes. You multiply. This one you know very well. That's the inner product. Ket. Let me say ket again. I showed that before. That's the outer product. Ket x. Let me see. Sorry. This is ket. Ket bra, right? We have a bracket that you know long time ago. That's the inner product. That time when we talk about bracket. What is it? Okay. This is the vector. This is the column vector. X1. This is the matrix. So when you multiply by this two vector, you get a number. Now to multiply two vector, what do you get? Not a number, not a vector, it's a matrix. It's a matrix. This is matrix. And this one is called outer product. Why is outer? What does it mean outer? Outside. What is inner product? Inside. You can do vector, you get a number, the number is inside. You only have vector. You multiply by two vectors, somehow you get something completely different. It's the operator, matrix. And we will see that exactly how we do projection. And that's how you, when you put in the qubit input, you can figure out how to measure it in by projection. Now, what else? So we have bracket, and then we have a gap bracket. That is gap bracket. How about gap? Gap. Can you? This is column vector. That's like, so like a column matrix. This is another. Can you? When you multiply two matrices, this one to another one, this have to be equal to this. Here, this row is n, but this one is 1 that you cannot. But we need to multiply. We need to multiply. Why? Because we have, if you have 1 qubit, you don't need. But you have 2 qubit, you need. And computer only have 5 qubit, 2000 qubit. So how do we represent? How do we represent? This comes from 1 qubit, this comes from a qubit, and this will be the superposition of 2 things. So this product is called the tensor product. Notation. This is for cat, y cat. What is that? What is a cat? A cat is a qubit that you input in your program. But you know, you have more than 1 qubit, that even at 2 qubit. You put in series or in parallel 2 qubit, it will come out a mixed qubit. And how do we represent that big qubit? So it turned out to be called the tensor product. So let me remember, if you remember Kronecker product of matrices. Vector is a special case. How do we multiply 2 matrices with different size? Suppose that you have A is matrix AJK, J from M, A, Mn matrix. And you have a B completely different. With is, let's say, 3P plus Q. So how do we multiply 2 matrices? Kronecker tells us you can multiply both of them, regardless of the size. And that tensor means straight up. You have one vector here. You have another vector here. When you put them together, big one like this, spread them out. That's what they call tensor, means like a tensor. Okay, so that's the name. And so what it is? How you multiply by the 2 matrices? Otherwise, you cannot see how the even 2 qubits look like. Okay. A multiplied by B equal this new matrix A11B, A12B, all the way to A1NB, A21B, A2NB. The last one is we have M1. What is it? Let me look for you one term and see how big the matrix is. U1. So, what is this term? A11 is a number, real or complex. Multiply with the B. See? How big? BQ, right? Okay, so you multiply one of them, so you get the following matrix. Let's multiply number 8. That is only one block. You see how big the matrix is? It will be a huge one. The first block here in this matrix. The second block is when you multiply this one with the matrix. Just put the matrix in here, stuck in here, stuck in here, stuck in here. You have this whole thing. And this is Kronecker did that over 100 years ago. Kronecker is famous by saying the following: God created an integer. Right? That's why you have 10, right? You count, right? You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No more, then you go back. That's why you have 11. Okay? When you're 10. That's why you go 10 and go back. And that is from God. So I give you the fact. But the rest is the work of man. That's the next concept. Kronecker is favored by saying, God only gave us the number 1, 2, 3, 4, 5, up to 10. Minus 1 is not God. It's you. 1/2 is not God. It's you. All the rest are the work of man. God only gave us the integer. He doesn't give square root of 2. Okay? All of that. But anyway, so let me show you easy, because this is how we apply to two things. First of all, suppose that you have 2 qubit computer. Remember that the equivalent of a classical one is what? You have 2-bit computer. That means you can input two numbers. 0, 0, 0, 1, 1, 0, or 0. This is a 2-bit, okay, 1. Okay? That is a 2-bit computer. So 2 qubit, then you can, first of all, you have to, you know what it is now, right? That is the get vector. 0, 1. Go to 0. This is a classical computer. This is a quantum computer. So the 0 is become a vector, and that vector you can, if you fix, that will be vector in the same thing. Okay? And the get vector for 1 is 0, 1. Now, so if you have 1 qubit, only 1 qubit, So what is the input to come in and what is the output come out? Come out to be of the form, okay. Example, you know why I change to AB and not alpha beta? You confuse with parameter. Okay, there's no parameter here yet, okay? It's not parameter. This is amplitude. Here AB are just like the wave, I explained already. Okay? You have a wave. The wave has the amplitude. Okay? So these are complex numbers because we present wave by n. So this is a qubit. This is 1 qubit. Now you have another one. Suppose a 2 qubit, so you have C0 plus D1. Then they come out to be what? Remember over here, if you have 2 qubits, you can take 2 qubits, so you put in 0, you put in 1. Okay? You can have 0, 1. So here, the 0 there is this, and the 1, so easy. So first of all, this is in situ. The vector in situ. The basis here is in 0, 1. So a linear combination of the two is in here because this is the vector space. Okay, but don't forget, it is a qubit, so A and B cannot be arbitrary. It's inside. A and B have to be such that A squared plus B squared equal to 1. It's not a convex combination. It's not a convex combination because it's not A plus B equal 1. But this is the probability of seeing the 0. This is the probability of seeing the number 1 when we make measurements. So if you have 1 in here, so what you put together, what is it? It's not Cartesian product. In classical probabilities, that's the Cartesian product when we talk about joint distribution. You have two spaces, so you put together just one from here, one from here. Okay. But here in quantum mechanics, it's not like that. It is in the tensor product of the two. What is that? That comes from this tensor products. So let me give you what is the tensor product. What's that? What is the definition? This is the vector 1, 0. Okay. Tensor product is 1, 1, 0 equal. Straight out vector. 1 times this. Okay. And then 0 times this. So it's equal to 1, 0, 0, 0. That's what we call 0, 0. That's what we represent 0, 0. There are 4 of them. Dimension 4. How about 0 tensor product with what? 1, 0 tensor product with 0, 1. That is 1, 0, 1, 1, 0, 0. And we call that 0, 1. Do more, then we are done with how to see Attention, the product is not commutative, just like matrices. What is it? Zero, zero, 1, 0. We call that 0, 1. 1, 0. That's what 1, 1. Zero, 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 1. And that's what we call 1, 1. So let me try it out and keep the 4 basis computational of 2 qubit. 0, 0, 0, 1, 1, 0, and 1, 1. Just think about it. Classically, you put in 2 number qubit, you have 2 qubit system. If you have 2 numbers, so you can write out 0, 0, 0, 1, 1, 0, 1, 1. Okay? They're all numbers like that. So this 0, 0 is a vector. So the 0, 0 is represented by this. Nothing fancy. That is a tensor product. We'll say the following. If you have a 2 qubit system, we'll see how qubit is if we have 2,000 qubits. Okay? We have a 2,000. It's complicated, but it has advantage. So that we have everything at the fundamental level. That means we have only 3 kinds of multiplication. You have cat by cat and bracket. You need that. We have and we have arbitrary number, whatever. That's the trick, just like addition in classical one. You know how to add, you know how to multiply, and let's say you know how to divide. So these are the 3 properties that is everywhere in quantum. So you will see just like that. And the reason is very clear. In order to represent the state. So what is the state? 1 qubit that you have. If that is 1, then you put it in. Rather than put 0 or 1, you put this in. In computer, you put only either number 0 or number 1. Let's say 0. Okay? You put only 1. Here, you're putting into your computer this qubit. So if you put 2, so what is the qubit? In other words, what is the form of a 2 qubit integer register? The state space containing this is C4. So it has four basic vectors. You know the form. That is the vector in C4. Now C4 has four bases. This. This is the basis of C4. You can see the basis. If you don't believe, you take this one, you take inner product with this, it will be 0. Number one is orthogonal. All of them orthogonal. Second one, x1, this form of orthogonal basis was C4. So these are the factors of C4. Then we will see at the end of today that depend on the way they look at. When you read quantum computing or you, there will be two main concepts that you have to pay attention. One is called superposition. This is superposition. Actually, for one qubit, either you are here or you are here. Okay. Just like your flip a coin. It's either head or tail. The only difference about quantum mechanics is to perform an experiment. Like you put it into your computer. It's not in here, it's not in here. It's in between. It's a form A, 0, B, 1. If you put it in, it will be like this. It's not here, it's not here. And this is called a superposition of these two basic. Superposition is just engineering term. For us, if we like, it's just a linear combination. Three combination. That means depend on anything where it is, with a very specific meaning. This is the state that you put it in. If you want to know it's here or here, you cannot look at it and see. You have to make a measurement. And the measurement you want to know is that it's 0 or 1, you have to project it on this one. Okay? So, projection on, think about this like a two axis, okay? Like a two axis. This is 1, let's say 1, 0. This is 1. And you have a this thing. You want to see? This would be this one. If you project it, so how you project on 0? Let's say. You do that because what is it? 1, 0. Time 1, 0. That you get a matrix. That matrix is 1, 0, 0, 0. That is a projection on this. That is projection because if you, let's say, x, y, this is on here. If you do this, so what you get? You get 0. That means actually, this one, let's say from here to here, is x. Okay? From here to here is y. So this point, x, y. But when you project it here, the y is 0. Because it's on this axis. So multiplication is not what I will write on and that's why you do. That's why you need it. Get and bra give you the projection. So let me, first of all, we have number, look at C2 first. Gate. Classical computer. Inside the computer, you put it in, let's say x equal 1. And you want it to come out to be number 0. The opposite of 1 is 0. You put it in 0, you get out 1. This is the NOT gate using Boolean logic. Okay. Okay. So Boolean logic. Intersection and complementation. So this is the NOT. This is the OR. This is the AND. Adding, this is adding. Now the question is, now this is the quantum knot. You put on what? Suppose that you put in 0. You want it to come out to be 1. You put in 1, you want it to come out to be 0. Not done. What makes them do like that? I don't know how they do this. In classical computer, how engineers do that? Turn on and off. That's why you only have 0 and 1, because the machine do for you. The machine can only do for you. You can write out anything, but the machine cannot duplicate what you want to do. You cannot do the machine. But the machine can only tell 0 or 1 by turn on or turn off. Or normally they will use the voltage. So the circuit has a voltage. So they make a convention. If the voltage is less than 1 volt, you call it 0. More than 1 volt, you call it 1. So the machine will turn on and turn off. You do the system so that you put it on 0. If you want to be 1, this one will turn on so that the thing will come out to be 1. Okay. So the question here is, how we tell the engineer to do that for us? First of all, you can see what the difference. In the classical one, there's nothing. It's just turn on and turn off. But here, you go with a number. This is not a number. This is the vector. And the output is also a vector. You transform a vector to a vector. How do you do that? Matrix. Multiply this vector. You want that to be 0, 1. So tell me what is ABCD. That's all. Okay, so what is it? This is the matrix. A gate is a matrix. Now the first thing to observe. A quantum gate is a matrix. Depends on the size. If you have 1 qubit, then the matrix is 2 by 2. That way, matrix and quantum matrix. So the question is, what is ABCD to put in here? Now it's so again in matrix, call it A. But this matrix have to be unitary matrix. Not any matrix. The matrix have to be unitary. That means it have to preserve the distance. So what's the distance? Okay. This is a vector. Okay. The image you put it in. It's of the form what happened? No problem. Don't worry about it. This is a vector. What is a vector if you write down in this basis? That's the vector. This is alpha with respect to this axis. This is beta with the axis. So the line of this vector on inside. The norm of this vector is the inner product of the vector by itself. Beta log. That's the norm. This norm has to be equal to what? Why? We say many times already. This is the amplitude. Just like amplitude, like the intensity of light. If the intensity is very strong, then that color is more likely than another one. This is the probability when you project, you get the 0. And this one is when you get 1. So when you put in alpha 1 plus beta 1 into your Q0, okay, you know what it is. You're going to get out whatever it is. But the probability has to be unchanged. Okay, because you're not doing anything else. You're just changing things around. Alpha and beta have to be the same. So the matrix has to be unitary matrix. That means the following. In this way, anybody have a course in linear algebra, you should remember what is. Let's say a 2 plus 2 matrix is unitary. That means in isometry. Isometry means preserve the length. Preserve the length. I'll give you an example. Rotation in the plane. Suppose I have a point here. And you have another point here. This is the distance between the 2 points. Okay. If you rotate crosswise with angle theta, the distance between these 2 points is the same as the distance of these 2 points. Because of rotation. Everything in computer you will see is all rotation. Because rotation is the only way that to move things, but you don't change the distance. Okay? This is from here to here, right? Same from here to here. Okay? The angle is different, but the distance is unchanged. So isometry means preserve. Okay? So definition. A is unitary if the inverse exists. In other words, the determinant is not zero. And the inverse is equal to the transpose. Two conditions. A matrix is unitary if it has inverse, and the inverse happens to be equal to its transpose. And if you have that, then this, so a gate is very good. You want to design, you have to tell engineer how to design the gate for you. You have to tell him, here is matrix. Just implement that matrix. So let's see what is the gate for not. Simplest one first. Quantum knot gate. Quantum knot gate. Let me give you by the way. Quantum knot gate. Try that. Okay? You can see it has the inverse. The inverse is equal to the transpose. And let's see what happens. You put it alpha 0. What do you get? And that is into the reverse. Reverse that. Okay, how to get this one? This one is easy, so I can get right away. This is how they put into the quantum to get the knot. Now, every rotation, what is it? This is the case where theta that you rotate 90%, 90 degrees. Rotate 90 degrees to reverse this cubic to the for many reasons. For example, if you want, suppose that to prepare alpha is much bigger than alpha and beta. And you want to come out to be alpha, you want to come out to be 1, then you do the knot. So the chance for you to get number 1 is much bigger than the chance to get number 0. Now, think about rotation counterclockwise or any angle theta. Then rotation. You know that this, we just say that this rotation is isometric because suppose you have 1 point here and you rotate to here. You rotate here, this distance is still equal to distance. So what is the matrix? People are studying geometry, they are concerned about that. We are not talking about geometry, we talk about quantum computer. We talk about what is the machine for us to build a gate. So here is simple program here, using complex number. find out what is the transformation, what is the 2 by 2 matrix, we do the rotation of any angle theta. This one is theta equal 5/2. So here is my proof. Okay. Okay, next. Think about it x1, like alpha beta, if you like. The point x1, and you have to rotate. So how to rotate that? Okay. For every theta, every angle, we have the following: I theta equal I theta is everybody knows, right? It's cosine theta. So, and you can see that as the what if e equals 1. So the normal product is 1. So if you multiply, you have an xy, and you write out x plus iy. You identify the vector with the complex number. So if you multiply this with e to the I theta, it has that means it preserves the distance, because this one absolute value is equal to 1. So if you do that, so rotation of angle theta counter clockwise go this direction, not the other one, counter. Okay. Then you get the following point. That is how you multiply by this, meaning you make the rotation of angle theta. And what is it? If you write it down, it's x plus I theta times cosine theta plus I sine theta. You write down the product and put everything in one side with the other side. And then I get x cosine theta minus I theta plus I x sine theta plus y cosine theta. So you can see the transformation is xy with this vector. So what? This is the matrix A times x1. So what is theta? What is the matrix? When you plug it in, it gives this one. That is simply A theta. This is the rotation of angle theta. And that is the matrix. You can see that cosine theta minus sine theta, cosine theta. You can see this is a unitary matrix. This is the matrix that when you transform a point xy to another point by rotating counterclockwise in angle theta. So you can see if theta equals 5/2, you get this. But you can rotate any angle. So let's do it 45 degrees and see what happens. You will be surprised at what it is. So cosine was I checked it here. If you look at any calculus text, cosine equal to sine 5/4 That is equal to 1 over square root of 2. Any calculate that. So, okay here, you get okay. That is rotation 45 degrees. Now, if you multiply it by itself, you get what I just erased. What is it? Not going. So what is it? Square root of not going. Basic in computer that you don't have in classical computer. What does that mean? Square root of naught. Square root of naught is a matrix. Think about the number. What is the square root of number A? Is the number, if you multiply to square it, is equal to 8. Square root of A times square root of A equal 8. This number is called the square root of 8. So this is the matrix is the square root of naught. This one. This is new. I remember I will send out 3 papers for everybody to read. The first thing you see that is the square root of naught. So after this, when you go back and read that paper, not only to know what is square root of naught, and we will see how we use that for computing. We never have something like a square root of 8 in classical. So it's nothing weird to you now. When they talk about square root of 8, you know what it is. It is a matrix. Everything is a matrix. If you think about this. Put 2 things in parallel. Don't measure it. Continue. What do you get? Don't measure it. Okay, because if you put through here, it come out. You go through here, you go through here, you go through here. Okay, so let me try this one. Suppose that I put it this one in. This one means 1, 0. That means alpha equal 1 and beta equal 0. Put this one through naught, and for this one, I will get this one. That means I get it for sure, 100%. Because the 0 is not complete. So you can see this one, you put it in. You get the other one. for sure. Because if you don't do that, over here you might not get. You want to get something sure, then that is how the square root of naught is using in quantum calculation. You can put in parallel to it, or you can put in series. Now, we will do something very interesting for you. Hadamard gate. You will see them everywhere. You will see the one more gate is very important, especially for simulation. Hadamard gate. They call it script H. Go right, we leave the H for the Hilbert space. I'm not confused. The Hilbert space is a space space. Hadamard is the following matrix. 1, 1, 1, minus 1. So we can take that is the geometry matrix. That can be used as a gauge. We will use this to do something very interesting in a second. But let's go to the 2-qubit system again. Okay, so you have that's the basic computation for 2 qubit. Everything is of the format A00 plus B01 plus C10. This is a superposition of a 2 qubit system. Beside the notation, the concept is not infinite. You have a vector with 4 dimensions, and this is the 4 bases. This is just a linear combination. Of course, to represent a state of quantum computer, you have to have A squared plus B squared plus C squared plus D squared equal to 1. The meaning is very clear. This is the probabilities that if you measure, you get this. How do you measure it? Projecting this one orthogonal to the axis 0, 0. This is the probability of getting 0, 1. If you want to see whether this is 0, 1, you project on it, but it's not sure that you get it. You only get the probability. So if you want something, you have to manage so the probability is very big, closer to 1, so you can get that one. Okay, everything is of that form. Okay, so this is, let's call this a state. This is a vector of C4 of a 2-qubit system. Now, how about this one? You can see some of this can be 0. Okay, not a complex number. No, A, B, C are different. Maybe, how about this one? Equal 1/2 0, 0 plus 1, 1. That means you have 1/2 0, 0 and plus 1/2 1, 1. This is one state. For 0, 1, 1, and the other one are 0. This one is 0, this one is 0. Only these two are, but they still have up to now. Second verse one. Can you remember it got there's only 2 words. Superposition and entanglement. These two things make computer better than classical. Superficial means if you put in two qubits, there will be two numbers, 0 and 1. Superficial means how many of them? Given. That's the first thing. The second thing, among these things, there are something very special that will never happen in classical computers. Correlated. And they come in the term of physicists. For us, is correlated. Like Puran and Vero and Gokula. Correlated. That means, you say, question is, two types of state. One is where did it come from? We input just like in computer, you have a 0 and 1 as your disposition. So you put a 1 and then you put a 0. That's why you have a 2. This system can handle. You can get a number like 1, 0. Okay? Here, you are, let's say, A 0 plus B 1, and you take another one, C 0 plus D. This is for the first qubit, this is for the second qubit. Okay? Just think like if you put in 1, then you have to put in 0. X1 is only from 1 qubit. So you put this 2 1. Then this 2 1. What's that? Tensor product. You do this, you get one of this type. You tensor two things, and that is very important. Linear. Everything is linear. Because a vector is like a matrix, is linear. So it only moves the basis, the A, B, C, D just follow. This will come out to be something. Okay? You can come out to be. Now let me change the number. Okay? This is from the first qubit. This is from the second qubit. And together they get one for the two systems. Okay? That's not interesting. The one that we really want is this. You want a stay over there, whatever, not same ABCD, okay? You want something like this. You want something like this. But it does not come from here. Because they are entangled. And we want to create them a lot. And why is good, I will explain. That's the advantage of quantum computer and classical computer doesn't have. You cannot create anything for anything. So here is the example. This is a special case of something like this, okay? Only this one 0, this one 0, only these two. The question is, can you find two vectors like this and give rise to this? If you cannot, then that is entangled. I give here, to show you everything here for you to do, so you can see. If not, this is an example. We call it a fail state. By the name of the guy to find out very good. All and do it. And they form the basis. So we don't have to look for, we just want to create. So with that, let me give you an example that how we use this to create really random number for simulation. Because remember, what you do simulation in economics or anything else. You want to find out a random sample from some variable x, and it has a known distribution. Known. You have a random variable which has a known distribution, and you want to have a random sample by simulation. You know what to do. You look at it, you know that x will be same distribution of the quantile of u, where u in the uniform 1, 0, 1. That's why how you do simulation. You pick up a random sample. This is called pseudo random number generated by your computer. They are not really random. Okay? They almost random but not random. You put a button on the machine and you get a random sample from 0 to 1, uniform distributed. The function f is known, then the quantile function is also known. You plug in the u in here, you get R1x. So like x1 is equal to f minus 1 of u1. And this is the random samples that you do by simulation and not go out do the real data. So now the quantum computer can improve this a lot because this will no longer pseudo, it's really random. Really random. So what is the machine will give you the random number. So here it is. Okay. Harama matrix is this one. Why is Harama? Harama is a French mathematician. He used this one for something else. It turns out that this matrix is the unitary matrix that we can use for quantum computer. Now, let A be the identity matrix. So let's take the tensor product of these two matrices. This way, the way, if you take that one, you will have a tensor, a huge matrix. And what you get is the force. That is one matrix. Let me just A by A first. This is the gate for one qubit. This is for 2 qubit. If you do the tensor product of these two one, you get the tensor, you get a gate for the 2 qubit system. And if you apply that, for example, to the vector 0, 0, what you get out, I will give you. What does that mean? Simple entities. This is uniform. The probability of getting this is 35%. It's 1 over 4. Because this one is like this is for him. Probability of getting this so you get 1 4, 1 4, 1 4, 1 4. This is Harama matrix is the one that they put in into the quantum computing for you to generate the real random sample for simulation. That's what Richard Feynman said before. That if you want to simulate real thing, the real thing is not classical. So you cannot use classical machine to simulate something which is different. You have to use the same thing from the real thing in order to mimic what is going on. So the simulation is simply based on the fact that you can, even for more than two numbers, okay, so you can do tensor products and time. Let me say something, then I want to ask a question to you. And then, okay, let me do this. What does that mean? What does that? You can see everything here. What does that? So I put in the intention. Let's take this example. This is entangled state. Entangled means correlated. You can see right away here. I have two qubits coming in. So let me measure one qubit, one by one. And suppose I get number one. I stop. Because I know the next one will be one. Because it's only this day or state. So if I know the first one is one, I know the whole thing. Because if I know the number one, it is here. Okay? It is here. It's not this one. Exactly not. You only one qubit. If you measure the first qubit, you get zero. You know this one. Otherwise, you have to check all of them for one. Is that 0, 0 or not, 1, 1. So this is simply the example of the entanglement that they always explain. That there is correlation between the two, very strong. Okay, if you do over here, you know the whole thing over here. And that saves a lot of time for computation. Okay, one more thing, so I want to stop for a question. So, how many gates we have? We have a NOT gate, we have square root of NOT, you have Karama. Now we want control NOT. These are the four main things. Control NOT means for two words. For example, you come in for basic. This is, don't forget, this is the gate, it's a matrix. The matrix only operates on them, not on ABCD. If ABCD are number. Okay? It's linear. That means A 0, 0, plus B 0, 1, plus C 1, 0, plus D 1, 1. When you apply it to A, it's linear. That means it will be A times okay, it's only operate on the vector. Not on A. A is just linear, it just come out. It's just the so you want an A so that when you run it, it operates on this one, this one, this one. Suppose it operates on the first one. you want to control, it's a knot. But it's a knot, you want it's a knot for the second one. And the first one, you control. What does that mean? You control, that means you can fix. That means, let's say, if it's 0, don't change it. If the first one is 0, leave this by itself. So, if it's 0, you control. If 0, leave that itself. And then if it's 1, then you do something. Whatever you want. Like if you want to be, if you call it control knot, that means you choose it. What is the knot of this? Okay, it's not of this one. You make that into the knot. Okay, if you use the one, you change the second one. Let's say you change the second one to 1, and if this is 1, you change this one to 0. That is called control knot. Control knot is of the following form. Everything is in a text. Call it control knot. It's a huge one. And now here, let's say you see, and here is your knot. The knot, that is the knot that we have. The knot is 0, 1. It's not there, right? This is the tensor product on 2 qubits. The whole one is for 2 qubits. 4 qubits. So like the dimension is bigger. And this one is for 1 qubit, not for 1 qubit. If you put in here, this is the keyboard. We'll do things like this. And if you do that, you will create control knot for you the 4 bases entangle. If you take this matrix, you have this matrix. See now, control knot. Apply. You put into that 0, 0. You put into that 0, 1. Put into that 1, 0. You put in that 1, 1. The first one you put like this. So you can see on my thing, these are the 4 entanglement states. And they are 4. So for 2 qubits, that's all enough. We need only 4 bases. And they are dual bases. That means 2 by 2, they are orthogonal. And the length of each one is equal to 1. So they are entangled. So what you do? When you know this entangle, you change it. That way, you not write like that. You not write like that. What does that mean? This is not number 1. This is just a label. You put in there anything you like. But it's not number 1. It's just, there are 4 there. Okay? If you have 3 qubits, then you have C8. There are 8 of them. So you have, like, the basis is get from 1, do 8. Whatever you choose, the basis is up to you to choose. And now which one we choose? We choose entangled basis. You see the advantage? The entangled beam. If you want, it is entangled state. If it's not entangled, if dimension is 8, how many measurements you need in order to find out something? 8. But in entangled, you measure what you know the whole thing. So if you put everything inside the basis formed by entangled state, the other one is just number. The vector that you try to if you want to find out it's, let's say it's 0, 0, 0 or not. Let's say for 3 qubits. You want to see this. How you project? Where do you project? Three-dimension. Don't forget this. If you want to find out in 1 qubit, okay, alpha 0 plus beta 1. If you want to find out in 0 or 1, you project this into this axis. But now this axis is like this. It's not an axis. It's a subspace. Remember Hilbert space that we learned. Subspace, like a 3-dimension. Okay, have a point in the space. If you project on here, then that is one projection. But if you want to project in this plane, not on the axis, it's on this subspace. On that subspace. So projection and subspace are the same thing. If you have a projection, you project where? Project to some subspace. And what is it? The closest one to this one. Remember, we have a theorem that we learned in Econ over 7. For every subspace, there's a point, a unit point in this subspace closest to this. And that is okay. So you can see how adaptable is useful. Because otherwise, this is 3, a subspace of dimension 3. That's good. We have to do that. But if it's entangled, then you might just need to do projection in 1 dimension, and you can find out the other one. Okay, so let me summarize so you can see things. And then next time we talk about what it is. So first of all, we're talking about for quantum symbol and meaning. Okay, so we have all the fact and all the transfer products and things like that. So these are the operations that we need to do between qubit. And we're talking about linear operator on your space. The language is linear on Hilbert space, not on another one. Hilbert space is very special. It has to have an inner product. So we can talk about orthogonal, we can talk about projection. Because if it's not, if it doesn't have scalar product, when you say you project where? And you project. Now we are very clear. I project orthogonal like this, or this one. It has one for me to project. So we're talking about, we do more next time, projection. Projection is not only the way to figure out if 0 or 1. It's more than that. Projection in quantum is what we call in statistics event. You toss a coin, the same thing that you put a bit to the computer, in either 0 or 1. Either 0 or 1. If it's 0, we say that the event is unrealized. If it's 1, we say the other one realized. Now in quantum, it has a lot of advantages. But because of the difficulty of quantum mechanics, we have to live with that. Whether or not it's true that if you don't measure, you don't know what it is. Nobody knows. Whether or not quantum mechanics is really express the reality of nature. That nobody knows. How can we see the electron on the photon? Okay? But we rely on them because I keep saying that 30% of the product in US is from quantum mechanics, including the photon. You like it? Successful? Right? Not only this, thousands of other things is made of quantum mechanics. So it's true or not, we don't care. It works. You don't have quantum mechanics? You don't have a photon. Just an example. A lot, and even in fact, they said it's more successful than classical mechanics. So based on that, we have to live with that. Everything here is something weird to you that we cannot play. That is quantum mechanics. And that is good. So now what we try to do is try to take advantage of that. Not to make the iPhone, to do something else. It happened 30 years. Started. Richard Feynman said that in 1982. But they really started looking around. In 1990, if you look at the book, okay, I really want everyone to look at the book that I wrote on humanity. In 1990, the first time they write out an algorithm. And the algorithm do the following. They take a problem which is NP, that means impossible in computer science, and we turn that into a P problem. So there are two examples. Factorization of prime number, that is very useful for security. Like that. First of all, they can write out a program that first is just a oracle. First is just an oracle. But whether or not the engineer can make the machine for you to do it or not. They can write out algorithm. After this step, after this step, after this step, you can get this in polynomial time. Okay? It's an oracle. That means maybe because you're not sure that they can make a machine for you to do that. But after that, they can. Very simple one, but they can. So that was 1990. How many years now? I said last time, 30 years. Not yesterday. How many years we start from zero until you have your personal computer? Exactly 30 years. 25 or 75. I came to Berkeley in the winter of 1975. I'm working on a problem with statistics, and we need to do simulation. You know what it is? I go to the computer. The computer is bigger than this room. The computer is bigger than this room at the University of California, Berkeley. No professor, nobody knows that on computer they have. Not everything about personal computer. Few places have computer, and you go to the machine is bigger than this. I still have that simulation. Only three months later, before the end of the summer, you know what happened? Apple, Silicon Valley in San Jose, just 20 kilometers from Berkeley. Who did that? A undergraduate student. He dropped out. He did not have a bachelor degree. He's just like a Honda. Honda make the car in the garage, okay? Don't forget that. He's not only he supply all the professor at university, supply the whole world. Possible to make personal computer. You don't know that. You do that in the garage of San Jose. That will have everything from that. Steve Jobs, you know that. It's only 20 years. So imagine that you ignore it. You don't have no iPhone, you don't have anything. Everybody. So this happened now in the 30 years now. Now it's possible. In parallel, they already have hardware about it. So if you don't pay attention to this, you only do the classical thing. And if you do the classical thing, someday you have a job. The machine will do better. The robot will take over your job. If the job is simply do like a machine, okay? Things like that, and you go now collect data, the robot can do. Put the data in, the robot can do. And they can do better than you and people. And faster, and they don't sleep, okay? They don't sleep, that's what they call it. So they not only the quantum computing things like that, but just think about if you ignore computer last century, you don't have everything nowadays. So I think that this is a good thing to. So roughly, all this one will be applied, and a little more for you about the airport. So roughly speaking, this is all I think you can say that the purpose is make you aware of the thing and try. I don't cover everything, but you can see starting how to be what we're doing here, and we have two purposes. Introduction for it. And we also want to use quantum computing. It's not only faster than the classical, it has something very different that classical cannot. It brings in quantum probability because the machine is random by itself. And that probability is not only we need to know a little bit next time to handle computing, but it can be used to improve all classical econometric model based on classical statistics. Because the tendency is that if we're talking about economic or any social science, it involves human. So when we will talk about black gentleman model rather than CAP-M, the reason is this: CAP-M, just like a classical computer, you don't have anything that you use it, but there's a lot of drawbacks. You know the drawback? Because we don't treat investor as human. We tell them we make them a machine. How you do it? Let's say how you do investment. It's uncertainty whether or not if you go up you might lose money, the risk, and they tell you, oh, the risk is standard deviation, and what you do is doing this. They forgot that they are human. You don't get. They use the black little man model is the Bayesian approach. Bayesian means human has factor inside. And the question is, if you allow human to make decisions rather than the machine to make decisions for you, if the machine can make decisions for you, robot can do. They can take over your job. They don't need you. It has to have some. If it's a problem about human factor have to be included. The question is, the Bayesian in the time, they allow you to put your information in, but they're still using classical covariance. Now, what is the new thing that we will try to learn, starting from next week until next month, is that the quantum covariance should be used when we involve human, and that is what I do. Okay, so I think anything else? Any question?
The question today,
No. Let me tell you this. We discussed a little bit. You guys are very good at using computers, but only at the service level. You don't know how they make the machine. You don't know how to write the algorithm. You only know what is the command and put number in. That's no fun. You can do it. I don't know. If you spend all your life doing that, you should understand what is going on. You're not building the hardware, but you should know what is in the hardware. You don't write out the algorithm, but you should know how they write out the algorithm to do that. So, mathematics is a must. We're not talking about know how to solve an equation. We're not talking about that. We're not talking about math. We're talking about the spirit of mathematics, because that's the language of science. What I say. You ask me, you give me an equation, ask me the solution. I say I don't know. I take time. It's not that you are a good math at me. See, the math is just the spirit, the way you formulate things, the way you look at things. But not you don't know. Writing algorithm is not doing math. The problem is you need the math language. Because that's a must. You know the symbol plus. 2 plus 3. They write out a plus. You don't think it's math. Okay? Now I just replace that by something else because I have different object. It's not 0. Okay? So I think that these things are not really number 2. Someone told me the following. Actually, is that correct? That so chapter people very good at operate on computer, but they don't know a bit. They don't know how you put in the bit, and they don't know the gate. Is that true? Well, we are not just restricted to looking at understand the command of the put the button and thing in. We should be a little. That is called technician. We should be a little like engineer. Okay, at least we should know. We should know. It's a magic. They put a button and 2 plus 3 and it come out of here. What the machine is doing? And that is not math, right? So all one here, one of the things here, this is necessary because in classical computer you might not need, okay? Because everything is simple, 1, 0, and they just do it all. But it turns out that if you do this because of the advantage of this computing thing, things are not that simple. So understanding how they operate, and that is even at the circuit level to still. But the thing we would like to do more is certain. It's not. This is not. Besides this is just the language. It's not. We're not doing any math here. We just try to say in the kind of algorithm, they will write things like this. They will write a command. So the command is not that. It's not like, oh, if you put the command and 2 plus 3 will come out to be 5. It's not like that. If you put a button, it will say you will get number 5 with probability 75%. Okay, so we should understand a little bit the thing like that.
Today class we continue from the last week, right? And in last week, Professor mentioned about the qubit and the meanings of the qubit. And I hope that in that class is more understandable and that. But for this class, we go in another stage of the countdowns. As you know, in the countdown, we need to know the qubit first as an input, and then we have to construct like what we call like algorithms to analyze the input that you formulate in the qubit inside. And now, the first thing that you need to know in the algorithm is gate. And in the quantums, not only in quantums, in the electric side, you will know that there are many gates. Like the electricity that move from one place to another place, you have to build like the gate. And then when you build the gate, you have to construct the circuit. I believe that Professor will talk about the circuit later, but now today class, just only the gate. And the gate that you learn here is just only 4 gates, right? Not gate, C, not gate, but and just
Control not?
Control not gate, yeah.
Oh, everything in the thing here. But if you read the other book, it's much more than that.
Yeah, right. So right now, what we try to do today is like formulate the gate first, and then we will build the circuit. The most difficult part is circuit, and then we can go to the algorithm in next week, as Professor mentioned. So you may see that there are many things today, and but if you carefully look the notation and the mathematics that Professor provides us today is similar. If you look at the equation that Professor wrote down in the board, is similar. So the only thing that we have to understand for today is how we build a gate, how we set up the gate, and how each gate are different. Sometimes, I think the book that I have sent you last week is the most simplest one. But if you want to get the book that in the Chinese version or in the Thai version, I suggest you to go to the electric side. Because what we learn here is same as the electric side. Exactly the same, but we just change. Also, actually the gate, the circuit, the bit, it has been introduced and proposed many years, more than 50 years ago. But now we just use the same thing that are already introduced, move and analyze by using qubit instead of bit, that's all, but the rest are the same. Okay, so do you have any question or do you have any things that you want to ask, like just a simple question, any question that why you come here, why this one is like that. No need to understand the mathematics actually. The mathematics here is just like the entanglement and the superposition.
The superposition of entangle is not, it's a concept, it's
Yeah,
not
it's a
math.
concept, yeah.
It's just the idea.
So-
There's no math at all. Okay. I don't win math. I don't write down equations, I don't want to solve solution. That is called math. This is only the symbol. There's no math at all.
So here now, Professor just mentioned about the entanglement and the superposition, and these two things will help you to estimate or analyze the qubit parallelly. So it will go parallel by using these two concepts. So if you want to know how fast these two concepts will help you a lot. Okay. Thank you.
Do you want to ask?
What is an entangled state? And what is the general idea of the entangled state?
Say it again.
What is the entangled state?
Yeah, entangled state is correlated. Correlation. You have two random variable correlated. That means you look at this one, you know something about the other one. Entangled. Disentangled, that means separate. I look at you, I know nothing about her. But if I look at you, I can know something about someone else. That is entangled. Entangled is put together. They are related. So just like a brother and sister, they entangle. Okay? Entangle means that entangle have to have a 2 qubit and more, not 1 qubit. It has to have 2 persons to be entangled. Have to be 2 qubit and up. Okay? So you have 2 qubit, 2 qubit. So in 2 qubit, so you put in 1 by 1. Okay? You input data in 1 by 1. Just like a 0 and 1. You don't put 1 and 2 at the same time. You put 1 and you put 2. But when you put 2 1, it becomes 1 2. It's just like you put number 0, and then you put number 1, then it comes out to be 0 1 together. Okay? So here the same thing. So you have 2 qubit. You put in 2 qubit, it comes out to be a tensor product of that. It can be in 2 forms. One is from this one and this one together, like this. Okay? But when something you put into one, the state come from not only one pair, from many pair in there. So that's why I say that it in general, a state in the 2 qubit, let's see the 2 qubit system. So you put in 1 qubit, you get something from 1 qubit, that means 0 or 1. This is 0 or 1. Okay? You put it in. When you put 2 in here, what is become? You put it 2 in there. It becomes something like this. 0, 8, 0, 0. 0, 1. You put 2 things in, it comes out like that. Okay? Come out like this. Now, the question is, when you look at this, what is the form? If this is, you come in one like this, on it, alpha 0 plus beta 1. Okay? And this one, let's say that one, alpha prime plus beta prime 1. You put this one, you get this one. This one can have 2 forms. Either it is equal to this tensor with this, or not. If this one is precisely this tensor with this, that is the pure state. They are independent. Take one from here, one from here. You put it in a very specific way, called it a tensor. But it cannot. If this is not like this one I said, you cannot find one like this and one like this. Then you do tensor, it equal to this. You cannot. This one is not the tensor product of these two ones. It is superposition of this thing. In other words, a state will have two components. Because we have two qubits, one from one qubit, two qubits come in form a state. So there are two forms. Either that state is separately formed from one by here and from one by here. If that is the case, they are not entangled. They are independent. Just think about two random variables. If you choose the product probability space, then it is two independent. But otherwise, it is correlated. So just like to talk about two things, x and y. That x is like the weight and y is the height. Okay. So whether or not is that two things are independent or dependent. So a state is entangled with the following. If you measure one, you have to measure the other. You know what it is. At the same time. Well, it's not easy to understand. We have to read book and think deeply into that. It's not an easy concept to understand, but roughly it's like that. Roughly is one of the advantages of computer that if we are interested in is faster, okay, beside other things. And then everybody has a question. If you are intellect, otherwise you say, I don't care. You say it faster, okay with me. I'm not talking about that. I'm talking about if you intellect and then say, how come it's faster? What made it faster? So if you ask that question, then the answer is because there are entangled states first. And you say, what does that mean? And the answer is simply this. They have an example there. Simple example to say, what does that mean? The state is entangled. State entangled when you have a state like 2 dimensions. It suffices to check very simple thing. You check one qubit and it come out to be number 1. Then you know over there is what is over there. You don't need to check over there. Okay. So it check like a saving time or something. Is that okay? This is not that, okay? I'm not talking about the symbol that they were putting in there. But when you say, oh, the symbol should not be mapped, okay? The symbol is not a symbol. You know, you never see that before, and this is the way to do it. And we have to do this exactly like this, because this is the way they write our algorithm, and we learn from it. So we need to learn the language that they do. There's no manipulation, anything here. It's just like a concept to represent it. And how you combine things the way that they do. When they write out quantum algorithm, they can write this symbol, this symbol. So rather than say, so it's not about the theory of quantum computing. It's just, I'm just trying to help you so that you can start reading book without saying, what is the tensor product and why like it like that. So you set out to use here and how to make it like this. So next time we'll continue on this, but we will focus on probabilities for computing and also for modeling. We have two purposes here. The simplest one is using classical econometric like gap model, things like that. The second one is we want to modify and we have a very good example that everybody should know. Gap model, when we improve a little bit with the right model, another way to make that. It's just like the gap model plus basic Okay, even with that alone, if you apply quantum computation, you can get a lot of research out there. But we can go a step further. After doing that, we will extend like innovate to the quantum model. And that is very simple because simply replace the Bayesian by quantum computing. So now, no question? Not now. No, if anybody interested in quantum mechanics, it's a very funny, Okay.
So that repeat it again. So today class, okay, just the concept again. Okay, but the concept really you're not understanding yet the notations and some concept that professor has give to you today. But I hope that if you go to check from the I mentioned before the electric side, you may get something more. Okay, the electric side. Okay, the circuit, okay, the circuit, and how the electric is moved, electron move along the line before they go to the circuit. It's like that. Maybe if we don't have any questions for today, maybe we have to say thank you to Professor for his lecture today. He spent a lot of time to prepare this seminar for us, okay?
I do this, don't worry, don't thank me. I do this, I for myself.
Yeah.
The best way to learn, if I learn and then no place to talk and I don't learn. So the best way to learn is to teach. Don't forget that. Because if you learn by yourself, you don't worry about, oh, they might ask a question. If you learn by yourself, you say, oh, complicated, okay? You don't look. But if I teach, I have to understand what happens if student asks. Okay? So you learn better when you are going to teach. So it's just my pleasure to do it.
Anyway, but thank you so much for listening.
Okay, next time, study quantum probability.
Yeah.
That how to handle that alpha and beta. Okay. For two reasons. And after that, I think that you will have all enough to do. Thank you, Professor Song. Yes. For question from Professor Song. Yes.
It is very interesting for this position because the idea is that I'd like to ask you that because this position is actually by Schrödinger equation. It is a linear combination of the state and the state is the solution. And because this kind of for example, linear combination. And it happened to be happening at the same time. This is like what we call because of the superposition, that the quantum computer can solve the solution because any linear combination of the state, which is going to be the superposition, is also a solution. And like quantum computer is so fast to get a solution.
Yes, the superposition allow the computer to operate like a parallel computation because they have more than that. And also, we are very lucky for computing here. The dimension is finite, so everything is finite. Because the Schrödinger equation is infinite dimension. That's why they're talking about the infinite dimensional space. But the reason for superposition is the fact that because in that what they call It's called the wave function because it's like a wave.
Yes, yes.
Yeah. So that's why they have a superposition and then superposition of this going over another way. So forth.
Okay, thank you.
Yeah, thank you.
So the next seminar we will held on next Wednesday at the same time in this room again. Okay. So
And
that
you will have the handout tomorrow.
yeah, and then I will send all of them to
I just send you.
Yeah, just send to me and then I will forward to
The
you.
handout is for the two
The
next two
next two.
in one topic. It's initiation to how you can, because we keep saying that quantum computing is random, so we want to have an idea about what is random and how we do it in quantum computing and modern.
Okay, so thank you again for listening.
Okay.